Uh, Exam 4 on chapter 14 and 15. We're going to be working from the sample exam document. And I'm just going to take them in order and discuss each question as we come to it. So how about that? So question number 1. And these may be somewhat in order, chapter 14, then 15. There's no guarantee. Number 1. Which atomic orbital contributor has 3 nodes? These they look like pi orbitals, but they don't have to be. They can be hybrid orbitals also. But they are all, notice they're all parallel, and they're parallel orbits in the ring structure. So in order to find a node, all you need to do is, well, first recognize that when we draw an orbital like that, that's polarized in one direction. This one is polarized in the opposite direction. So their interaction is anti. And you always have a node between these differences here. So those two are going to present a node. So anywhere you have a switch from one to the other, you have a node. When you have, if we had another one on this side, like that, there would be the potential for overlap. So there would be no nodes there. All right, so if we're looking for one with 3 nodes, we just need 3 flips, right? Roman numeral 1 has 2 flips. There's a place there and a place there. Roman numeral 2 has a flip here and a flip here. That's still 2. We have a flip here and a flip here. That's only 2. We have a flip there, a flip there, and a flip there. That's 3. And we have 2 here. So Roman numeral 4 would give us 3 nodes. And remember what a node is. A node implies no electron density. The probability of finding an electrode in a node is 0. Doesn't mean there can't be any there. It's just probability says that electrons do not occupy that space. All right, this is going to take forever. I think we need to treat that board. All right, hopefully that'll make it more erasable. That's a little better. Okay, number 2. So how many areas of constructive overlap, right? Constructive versus destructive. This is then a discussion of interference. And it's a similar discussion to problem number 1. But now we're looking for places where orbitals can overlap. That is, meant their phases are aligned. So we get an overlap in the first 2 on the left. We get an overlap in 3 and 4 orbitals, and we get an overlap in 5 and 6 orbitals. 1, 2, 3, 4, 5, 6. No, 6 and 7, excuse me. 6 and 7. So there are 3 places where we can get constructive overlap. All right. Number 3. In a nitrogenous base, guanine, how many pi electrons contribute to the aromatic pi system? All right. This is a fused ring system. It's not only that, but it is heterocyclic. That is, all the positions in the ring are not occupied by carbon, right? Homocyclic could be anything, but in our case, it would be carbon. So if we draw the molecule, we have to draw it like this. I always start off with carbons and then I substitute. Right? So we got carbon here and here. We have nitrogen here. Yes. We have a nitrogen here. We have one here. And we have one here. And then we have an amine group here. And we're going to draw in the lone pairs so that we can account for all of the electrons that enter into the conjugated system. All right, let's put the double bonds in there, here, 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 and we've got lone pair here, and here's where we connect to the sugar. And then we have a lone pair there, and we have a carbonyl group here. All right. If we had a situation where the fused rings were homocyclic, then all we would have to do is count up the double bonds, 2 for each double bond. Right? Then we could say that's how many pi electrons we have, and then we could use our Huckel formula and determine, assuming it was fully conjugated and planar, then we could decide whether it was aromatic. When we have heterocyclic fused rings, it's usually easier to take each ring separately. So we would take this ring separately and decide, is that ring aromatic? Then we take this one and say, is that ring aromatic? In addition, we have lone pairs. Let's see, we've got one here, one there, there. We've got 2 there, 1 there, and here. I think I've got them all accounted for. 1, 2, 3, 4, 5, 6, 7. 4, 5, 6, 7. Okay. But not all lone pairs contribute to the conjugated system, the pi system. So we need a way to figure out which ones contribute to the pi system. And it's been my observation that if there is a double bond attached to the nitrogen, then any lone pairs that it has are actually perpendicular. They're not parallel, so they can't be used. So this nitrogen has to be sp2 hybridized because it has 3 groups. sp2 hybridized. That means, well, let me make it even simpler. If you've got a double bond attached to a nitrogen or a carbon, that means that the pi bond in that double bond is formed from an overlap of 2 neighboring pi or hybridized orbitals, which means that any lone pairs are not available. You've already used the parallel orbital to overlap. So if there are any lone pairs, they are not available. they are perpendicular to the system. So this one is not available, right? There's a double bond there. This one is available. And this one is available. And this one is available. Okay? So if we're looking at just that 5-membered ring, what are the Huckel numbers? Right? This is the planar molecule. So what are the Huckel numbers? If n equals 0, 1, 2, 3, 4, then what is the Huckel number? Right? 0, remember? 4n. Well, let's see. I can do better than that. Four n plus 2 is a Huckel number. So it could be 2, it could be 6, it could be 10, it could be 14, it could be 18. Right? That would be the number of electrons in the pi system. How many electrons are in this pi system? 2, 4, 6. There's your Huckel number. This is aromatic. Okay? How about this one? When we go to the other one, we've got to decide which ones contribute. Well, we've got 2 here. We have 2 here, but that one is not available because there's a double bond attached to it, to the nitrogen. This one is outside the ring system, so that lone pair doesn't count either. But this one has no double bonds. That means this one is available. So we have 2, 4, 6. And this one's outside the system also. So we have 2, 4, 6. Again, we have aromatic. So if all the rings in a fused system are aromatic, then the whole system is aromatic. Okay, so we've determined that this is an aromatic system. Now we need to count up how many electrons are in that system. So here we have to be careful because we're going to count all the electrons. We used this one right here twice. Don't count it twice. So we have 2, 4, 6, 8, 10. 10 electrons in that system, and it is aromatic. All right, that was number 3. Number 4. Leave that there. We might need the Huckel numbers again later. Number 4. Which term can be used to define a molecule that is cyclic, planar, completely conjugated, and has 4 pi electrons? Right? That's a Huckel number. An anti-Huckel number is 4n. Right? This is Huckel. This is anti-Huckel. Anything else is non-aromatic. So anti-aromatic would be 4 electrons, right? If we make this 1, n equals 1, then we have 4 electrons. That's anti-aromatic. So this is anti-aromatic. All right. Number 5. All right, this is which of the following molecules is aromatic? So in this system we have homocyclic, that is, all the positions in the ring are occupied by carbon. And now all we have to do is count up the number of available electrons. And we have to be careful that we don't miss any lone pairs that might be available. Right? So the first one is 1, 2, 3, 4, 5, 6, 7 is a heptene. Actually, it's a hept 1, 3, 5 ene. It has 3 double bonds, and one of the carbons is deficient. There are no lone pairs on that carbon, the carbon at the top. So that means we have all the conditions necessary for aromaticity. Roman numeral 1 is aromatic. Right? That's aromatic. How about number 2? 2 is linear, right? It fails on the cyclic part. That's not a ring structure. It cannot be aromatic. How about number 3? Number 3, we have to assume it's planar, but assuming it's planar, how many electrons are in the system? Well, one carbon is a carbocation, which means that there are no lone pairs there available. So that means we can only count 2, 4. That's anti-aromatic. So this is aromatic. Number 2 is non-aromatic. Number 3 is anti-aromatic. Number 4 has 2 electrons. Remember when we draw something like this, these are carbons, and if we don't put a charge anywhere, that means that this carbon has 2 hydrogens. No lone pairs. This one has 1, 2, 3. It only has 1 hydrogen, and this has 1 hydrogen. So there are 2 electrons here. 4n plus 2. So if we say this one is 0, that would be, okay, it has 2 electrons, but is it conjugated? It can't be conjugated because there's only 1 double bond. And it's isolated from the other carbon, right? So it fails in the conjugated condition. It is not, number 4 is not conjugated. So number 4 is non-aromatic. Let me think. Is that non or anti? No, it's non-aromatic. It's got the right number of electrons. It just doesn't, it's not conjugated. All right, so it is non-aromatic. Number 5. Number 5 has a lone pair and a double bond on adjacent carbons, right? So we have a single bond, and then a lone pair available. Now, is that lone pair in a p orbital? Well, if we look at it this way, that
from Charleston.
then we have a negative charge on that carbon, which means it has a lone pair, right? So how many hydrogens are attached to that carbon? Well, we need an octet, right? We need an octet. So we've got 2, 4, 6. That means we have another hydrogen attached here. That means that this carbon is sp2 hybridized. And this one is lone pair. No. It has 1, 2, 3, 4. This is sp3 hybridized, right? So it has no available electrons, pi electrons, no electrons available for overlap, right? So it fails there. That means this one is non-aromatic. It has it has 4. Oh, no, it's anti. It's anti-aromatic. It has a 1 times 4 is 4 electrons. But it fails in its conjugation. It's not conjugated. It doesn't have parallel p orbitals or hybrid orbitals that can overlap. Right? So that one is anti-aromatic. The only one that's aromatic is number 1. This thing on screen. There we go. Number 6. Which number of pi electrons can be defined as an anti-Huckel number? Well, it would just have to be 4n, right? So that means if n equals 0, 1, 2, 3, 4, 5, then the anti-Huckel number, let's see, let's do it like this. Remember, anti-bonding orbitals have an asterisk. This is an anti-Huckel number. All right, so 0 here would be 0. 1 would be 4. 2 would be 8. 3 would be 12. 4 would be 16. And 5 would be 20. These are anti-Huckel numbers. So 16 is the only one in that group that fits. Okay? If it's not a Huckel number and it's not an anti-Huckel number, it's non-aromatic. It's a non-Huckel number. All right, number 7. Okay. All right, number 7. How many electrons are in the given molecule's largest conjugated pi system? Remember this molecule has a benzene ring here, right? There's your benzene ring. Then it has a branch like that, and it has double bonds here and here. These are conjugated. These are conjugated pi system. There are 2 pi systems in this molecule, and they're isolated from one another because there's a single bond here and a single bond there. Okay? So I have 2 pi systems. The number of electrons in the largest pi system, this one has 4 electrons. This one has 6 electrons. Right? So that's the largest pi system, has 6 electrons in it. All right. Number 8. Which atomic orbital contributor has the lowest energy? The lowest energy is the set of orbitals that have the maximum or the most of the selections, has the most positive constructive interference. Constructive interference means that the orientation of your orbitals is in line. In other words, if we have all of them like that, and they're just a string of them like that, then anything else is going to be higher energy. This is the lowest energy is where you get the most overlap, and that's number 5. That's Roman numeral 5, which is E. That will be the lowest energy. And if we drew I lost the term. Shoot. We drew the energy diagram. The lowest energy in the energy diagram would be the maximum constructive interference. Number 9. Which of the following reactions releases the least amount of energy upon hydrogenation? The one that releases the least amount of energy is the one that is most stable before hydrogenation. Right? So if we've got conjugated bonds, that lowers the energy. And even lower than that is aromatic. So we have the Roman numeral 1 has a conjugated system of 3 double bonds, or 1, 2, 3, 4, 5, 6 carbons. That would be a fairly low energy. How about the next one should be about the same. The next one should be similar. This one would be a higher energy because it has an isolated double bond, right? Number 4. Number 5 is an aromatic system. It will have the lowest hydrogenation energy, enthalpy of hydrogenation. So E, Roman numeral 5, is the lowest heat of hydrogenation. And all these are exothermic processes, right? So it's going to give off the least amount of heat because it starts at a lower energy. They all end up at the same place, right? They all end up with this structure on the right of each of the arrows. Number 10. Which term can be used to define a molecule that is cyclic, planar, completely conjugated, and has 10 pi electrons? That's definitely aromatic. Which of these following molecules is aromatic? All right. Well, let's take a close look at these guys. We've looked at number 1 already. This cyclobutadiene is anti-aromatic. It has 2 pairs or 4, has 4 electrons in pi electrons, which means it's anti-aromatic. So the first one is anti. How about the second one? How many electrons go into the system? Well, it's cyclic, it's planar, it's fully conjugated, but the pi electrons are not in the system. They're not in the ring. In other words, it's only got 4. So that one is also anti-aromatic. The carbonyls contribute to the conjugated system, but they're not part of the aromatic system. Number 3, 2, 4, 6, 8. That is 8 electrons, right? And 8 would be 4 times 2, which would be anti. That's anti-aromatic. How about 4? Right? It's cyclic. I suspect that this one may not be planar, but we've got 2 sigma bonds between those top 2 double bonds. That means it's not fully conjugated. Right? So 4, it doesn't matter if it's planar or not. It's not conjugated. So 4, being not conjugated, is non-aromatic. Because it has the right number of electrons, it has 6, right? But it's not fully conjugated. So it's non-aromatic. And Roman numeral 5 is planar. It has a lone pair, right? It has a lone pair up here, and it has those. Now, is that one aromatic? You know, didn't we see one of these before? right? That's 2,4,6. Hold on a second. Let's go back up here. Oh, okay. No, we were looking at a different one. Right. That's not fully conjugated. Okay. But this one, right? The cyclopentene, cyclopent was a diene, has 2,4,6. So this one is aromatic. Very stable. All right. How many pi electrons contribute to the aromatic pi system in cytosine? So look at the question. How many pi electrons contribute to the aromatic pi system in cytosine? We're being told that it's aromatic. We don't have to determine that. We just have to find out how many electrons are in the system. So it's either got to be 2, 6, 10, 14, or 18, or whatever. So let's make room. Right. And we've got this molecule, cytosine. Let's see. We've got here, there. Nope, sorry. Jumping the gun. There. And there. And there. And then there. Right? Nope. Missed it again. There we go. This one has a carbonyl. This one has a hydrogen and a lone pair. There's a double bond here, double bond there, and amine here. Okay. The aromatic system is in the cycle right here. We don't include these. We don't include these. There's no double bonds on either side of that nitrogen, so that lone pair is available. This one is available. This one is available. You know, we're isolated here with 2 sigma bonds. Oh, but that's not available. So we're told it's aromatic, but how many electrons are in the aromatic system? 2, 4, 6. There's 6 electrons in this system. How do we bridge the gap between this one and that one? Right? Okay. I have a solution to this problem in number 12 for cytosine aromaticity. So let's draw the structure. Let's draw one of the resonance structures first. Yep. Here. And let's see. Let's draw it the way they have it in the diagram. Go. Okay. And there, and here. So the way we get aromaticity out of cytosine is this carbonyl group is essential to constructing a resonance structure that shows us aromaticity. And here's how it happens. This lone pair right here is donated to this side, producing a double bond. And when it does that, then that carbon would exceed its octet. So we got to get rid of a pair. And the only pair that we have a chance to get rid of without breaking a bond is this one right here. So this one donates its pair of electrons to that oxygen. And what that gives us is this structure. There's our donated pair. And now that we have, and we can, when we count up the, if we calculate the formal charge on oxygen, remember oxygen valence electrons would be 6. And then we subtract 1, 2, 3, 4, 5, 6, 7. All right, so that's a -1. That gives us a charge on that oxygen. Now, what do we have in the ring structure? We have 2, 4, 6. 6 electrons, 6 pi electrons in the ring structure, and that's a Huckel number. So this gives us aromaticity. We got a fused ring here. Number 13. All right. Is the following compound aromatic, anti-aromatic, or non-aromatic? All right. First of all, it's cyclic. In fact, it's a fused, 2 cyclic fused rings. It's planar, right? Is it completely conjugated? It appears to be so, alternating double and single bonds. And does it have, how many electrons does it have? Well, since it's homocyclic, then we just count up the double bonds. 2, 4, 6, 8, 2, 4, 6, 8, 10, 12. 12 is 3 times 4, which is anti-Huckel number. This is anti-aromatic. Number 14. How many p systems does this species have, and how many p electrons does each p system contain? P there is a substitute for pi. So just think of it as a pi system. So how many pi systems do we have? Well, let's see. It looks like everything's conjugated from the ring all the way up to the amine group. Right? That amine has available pi electrons. So the nitrogen is part of the pi system. How many pi electrons does each system contain? Well, there's only one system, so it has 2, 4, 6, 8, 10, including the lone pair, 10 pi electrons. Right. 10 pi electrons. It's not aromatic, obviously, because it's isolated. These two bonds right here isolate these, but it is conjugated. It is a valid pi system. 15. Huh. Number 15. Is the following compound aromatic, anti-aromatic, or non-aromatic? All right. The explanation is the deduction. Now, what it doesn't tell you is it doesn't show you the lone pairs. And then a 5-membered ring with a sulfur right here, like that. A double bond here, and a double there, double there, double there. Okay. Remember, sulfur is like oxygen. So it usually has 2 bonds and 2 lone pairs. So we got a lone pair here, there, and there. Only one of those lone pairs is in a parallel p orbital that is available to conjugate. So we do have this one available, that one available, that one, that one, that one. In this case, we don't have to separate the systems apart like we did at the very beginning of this discussion. We've got 2, 4, 6, 8, 10. Right? 10 pi electrons. This is planar, cyclic, completely conjugated, right? Because we have this one, single bond, double, single, double, single, double, single, double, single, and pi electrons. So this one is completely conjugated and it has the right Huckel number. So this compound is aromatic. Number 16. Excuse me. Is the following aromatic, anti-aromatic, non-aromatic? Explain your answer. Okay. The compound is cyclic. All right. We met that condition. Is it planar? Yes, it's planar. Completely conjugated. Let me see. This has a positive charge. So what does that mean? That means there are no lone pairs. There are no lone pairs here. There and there and here and here. These methyl groups don't contribute at all. We're only interested in the ring structure. All right, so we've got a ring structure here with 2, 4, 6 electrons, which is a Huckel number. It's planar, it's cyclic, it's fully conjugated, and it has the Huckel number of electrons. This molecule is aromatic. All right, excuse me. Number 17. Give the 4 requirements a molecule must have to be considered aromatic. Right? We've done this over and over again. This one's simple. Has to be cyclic. Has to be planar. It has to be completely conjugated. Right? So even linear molecules can be completely conjugated, but they don't meet the other conditions, planar and cyclic. And it has to have a Huckel number. For n equal to or greater than 0, 4n plus 2 pi electrons in the conjugated system. Those 4 conditions must be met. Number 18. Which compound, C or D, would be expected to undergo heterolysis more quickly? All right. This is a concept we've covered before. The speed of a reaction tends to follow the reaction that produces the most stable product. So if we undergo heterolysis, and where would heterolysis occur here? Remember when we have an SN yeah no, an SN1 reaction produces the carbocation first, correct? So heterolysis here would occur at the bromine. It's a leaving group, right? It would produce the bromide ion and the carbocation. Okay. This particular carbocation is stabilized. It is conjugated with this system. So it's more stable. Whereas if we had the bromine on the other molecule, it had the bromine over here, right? Let's see. If we had the bromine, get rid of that. We had the bromine here, right? And it left. What we have behind is this, this, and that. Now, they're both of these possibilities are secondary carbocations. So we can't decide based upon secondary, primary, or tertiary. This is secondary, that's secondary. What this one cannot do is it cannot undergo conjugation. In other words, we can't produce a resonance structure for this one, right? Because if this one moves over here, then it puts a double bond there and puts a positive over here, and that won't work. But for this one, what we can do is we can go here, and that would produce that would put the positive ion here and a double bond there and there. That's a conjugated system, which makes it more stable, even though that's a primary carbocation. Actually, actually it won't go there. It'll go here. Yeah. So resonance has stabilized molecule C. So heterolysis for C will proceed faster. About 19. Is the following compound aromatic, anaromatic, non-aromatic? All right. This compound, is it fully conjugated? Well, the ring is planar. The rest of the molecule is not, so it can't be aromatic. We don't have an aromatic ring in this one, but it is fully conjugated. And how many electrons do we have? 2, 4, 6, 8, 10. Right. So we have the right number of electrons. We just don't have a cyclic planar system, even though it's fully conjugated. So this is non-aromatic. All right. 19 is non-aromatic. 20. We saw this one before. Right. The compound is cyclic. It's planar. Since it has these two lone pairs that are available, then we also have a conjugated system. But it has 2, 4. It has 4 times n, where n is 1 equals 4. That's an anti-Huckel number. So this one is anti-aromatic. All right. 21. How many nodes does the following atomic contributor have? All right. Right, just like before, all we have to do is find out how many places does it switch from one polarity to the other. So let's start from the left. We've got 1 and 2 has that, 2 and 3, 3 and 4, 4 and 5, 5 and 6, 6 and 7. We have 6 nodes in this particular arrangement. And this is probably the least stable of all pi systems, because you have 7 atoms and 6 nodes. How about 22? Well, we have a fused ring system. I think this is anthracene. I believe this is anthracene. Anyway, we have a cyclic structure. It's planar. The system is fully conjugated. We can see alternating double and single bonds. And it has how many pi electrons? Well, let's see, 2, 4, 6, 8, 10, 12, 14. 14. That's a Huckel number. This compound is aromatic. Twenty-three. 23. How many pi systems does this species have? How many pi electrons does each system contain? Well, let's see. Pi systems. How does the conjugating go? We've got a benzene ring, and then we have a conjugated double bond, and we have an amine group with a lone pair that's available. So that's 1, 2, 3, 4, 5 times 2 is 10. We have 10 electrons in this pi system, 10 electrons, and 1 pi system. It's a single pi system. Now, the benzene ring is aromatic, right? But the rest of the molecule can't be considered in the aromatic scheme because all the conjugated bonds are not in the ring, right? So only the benzene ring is aromatic, but the system itself is conjugated with the pi system with 10 pi electrons. How about 24? Which molecule would you classify as more stable? Explain your answer. Well, we look for the possibility for conjugation, right? In A, we can conjugate that lone pair on the central carbon with either side of the molecule, right? We can do a shift and create an alternate uh, uh, resonance structure, excuse me. Whereas with B, those double bonds on either side of the molecule are isolated from one another. Right. So, well, there's an alternate explanation in yellow, right? A would be more stable. Yes, that's true. We stabilize carbocations. Tertiary is more stable than secondary, is more stable than primary, all other things being equal. But you can also stabilize a carbanion with that same concept. And in addition to that, with that lone pair of electrons on that central carbon, you can also create resonance structures that stabilize it further. So this is not just resonance stabilized. This is a conjugated system on the left for A and not conjugated for the one on B. And in addition to that, the B we got a lone pair there. The B this is sp3 hybridized carbon, right? Because there's a hydrogen here. sp3s don't produce available parallel p orbitals, or sp3 orbitals are not in line with the others. So you don't get a conjugated system there. So that destabilizes B, whereas A is stabilized. All right. Oh, now we're going to look at some mass specs. All right. Number 25. All right. This is kind of small. It's kind of hard to see. But the question is, which one is the molecular ion peak? The molecular ion peak is the furthest to the right without considering any minor peaks to the right of the, so it's furthest to the right and it's the largest furthest to the right. And the reason I say that is because if you have an M+1 or an M+2, then you have to start somewhere, right? If you have a peak to the right, another peak to the right, it looks like there's a really very tiny one at let's see, 75, 6, 7, 8, 9, 80, at 180. So 179 would be the molecular weight of that ion. And then M+1 would be 180. All right. So Roman numeral 5 is the position for your molecular ion peak. Number 26. All right. Which is the base peak? The base peak is the tallest one, which is normalized to 100. Relative intensity of 100. Everything else is less than that. That means Roman numeral 3 is the base peak. All right. 27 coming up. 27. Question. Which atom is likely present in the molecule responsible for the following mass spectrum? All right. So now we're looking at the furthest to the right, and the creators of this question kindly identified the molecular peak. Right? So we look to the right, and what do we have to the right? Let's see, a 1, an M+2. M plus 2 is either chlorine or bromine. Okay, how do we tell the difference? We tell the difference in the relative intensity of each one. This one would be a 3-to-1. This one would be a 1-to-1. So we look at the relative intensity. The peak on the left, the molecular peak, is 3 times the height of the one on the right, the M plus 2 peak. So that's chlorine. Right. And let's see, 28. 28, which M divided by Z value would clearly indicate that a nitrogen was present in a sample. Remember, based on the nitrogen rule, both A and E have odd number masses. That means possibility of nitrogen. Right? B, C, and D are even numbered. They don't have nitrogen. So we have to decide between A and E. How do you do that? Well, if the fragment is 13 units, right? What's the mass of nitrogen, right? The most common isotope of nitrogen is, let's see, so 14, right? That's too big. So A cannot be it. There's no possibility of a nitrogen there because there's not enough mass. So the only other possibility is E. 155 is an odd number. That will be the one with nitrogen in it. Number 29. Which of the following statements is true regarding the information contained in a mass spectrum? All right, let's look at them one at a time. A, B, C, D, and E. How about A? The molecular ion is always the most abundant peak. No, it's rarely the most abundant peak. All right, so that one's false. B, the fragment with the most stable radical leads to the peak with the greatest intensity. What's a radical? A radical has an unpaired electron. Now, it may have a charge, but it doesn't have to have a charge. And most of these fragments that we've seen, well, we have actually the molecular peak. Oh, excuse me. The molecular peak is a radical, but it has a charge. So we can't just blanket statement say that the radical leads to a peak with the greatest intensity. Right? If it's not charged, it's not going to show up in the spectrum, right? So B is false on a technicality. How about C? More intense peaks represent more likely fragments. Yes, right? The more abundant they are, the more intense their signal. So C is true, right? We don't have a D and E are not one of the above, two of the above, none of the above, those kind of squirrely statements. So we could stop here if we wanted. But if we looked at D and E, we could see that they're both false. D says the fragment peaks detected correspond to both radicals and cations. No, they don't. Radicals do not enter the spectrum because they're not charged. What will happen to them as they go through the magnetic field? They'll just go straight on through. They'll miss the detector entirely. How about E? The most abundant peak corresponds to the compound's molecular mass. No. That's another way of saying A. So E is also false. All right, so we found our true one right there, C. Let's see, we're going to 30 next. All right. So A, B, C, D, and E. A, which of the following statements is true regarding the detection of fragments in an electron impaction ionization mass spectrometer? Okay. A, the radical fragments are highly reactive and therefore are easily detected. That has nothing to do with detection. The detector detects impacts, individual impacts on the detector. It wouldn't matter if they were highly reactive or not. And radical fragments will not reach the detector because they're not charged. Only charged species reach the detector. Remember when the beam goes through the magnetic field, it bends, right? If it's not charged, it's just going to go straight on through. Miss the detector altogether. Right? So A is false. And let's see, 30. Okay, B, the most stable fragment will be detected in the greatest abundance. That's true, as long as we are assuming the fragment is charged. The most stable fragment. Based on that statement alone, we can say it's true. Because it has to be detected. The most stable fragment will be detected. If it's detected, it has to be charged. And the most stable one is the most abundant one. C, fragmentation is random and unpredictable. No, that's not true. We looked at several slides during the lecture where fragmentation followed a pattern. It followed a pattern based upon stability of the outcomes of the products. D, the detector is unable to determine the relative abundance of fragments, only the molecular ion peak. No, all it's doing is counting impacts, right? So it can determine the relative abundance of all the fragments that reach the detector. The sample must reach the detector in a liquid state to be detected. No, they're all gases. They're gases because they're individual fragments. They're very far apart. That, by definition, is a gas. So these are both false. B is the only true one in that group. Number 31. Explain how you can use a mass spectrum to determine if a single nitrogen atom is present in the molecule. All right. One or more atoms in the molecule, nitrogen atoms in the molecule, based upon the nitrogen rule, is that the ion peak will have a negative or an odd number. No, it's not a negative, an odd number mass. All right, this is labeling. Which one is the base peak? It's the tallest one, the one that's set equal to 100, relative intensity. And the molecular peak is the furthest to the right of the major peaks. You know what? I think that's wrong. Yeah, that one's wrong. It should be over here, right? Because I can see another peak here, and I can also see a minor peak, just barely a minor peak at m+1 right there. So there's a correction. This is the correct value. Answer to the question. All right, 33. In a mass spectrum of an alkane, why does the ratio of m+1 peak intensity to molecular ion peak intensity increase as the number of carbon atoms in the molecule increases? So what they're saying is, if we have an M peak out here, then an m+1 peak out here, an N+1 peak out here will increase in relative intensity to the molecular peak, if the molecule has more carbons in it. Why is that? It's purely probability. The more carbons you have, the more chance you have to have the, if this is based upon C12, then this is going to be based upon C13, right? N+1. So the more carbons you have, the bigger the peak's going to be. Because the likelihood, the probability that you're going to encounter carbon-13 isotopes in the molecule is much higher with the more carbons you have. Let's see, 34. All right. Explain how you can use a mass spectrum to determine if a single chlorine atom is present in the molecule. We did that before. You need the molecular peak, and you need an M+2 peak. Right, that's about right. And the ratio of intensity must be 3:1. Yeah, this peak is 1/3 the height of that peak. That signifies, and with an M+2, that signifies chlorine. If we go to 35, then if this M2 peak is about the same height intensity as the molecular peak, then you have bromine. Right? So this is chlorine before, bromine now. All right. 36. Which of the following compounds will have a more abundant molecular ion peak in its mass spectrum? All right. Which one will have a more abundant one? Well, for this 2,2-dimethylbutane on the left, notice it's branched and gives us a like that. If the electron impacts break this one here, right, then these electrons are going to go over here and produce a free radical, and then and leave this one deficient. That carbocation is more stable than if we have 1, 2, 3, 4, 5, 6. 4, 5, 6. Like that. Anywhere we break this in here, if we break it here, we could get a carbocation there. That would be primary, but it would probably do a hydride shift and move over here. But still, it's not as stable as this one. And if it broke the other way, and we put this secondary over here rather than over there, then we'd still get a primary. And this would even be more unstable. So this will be the least stable, this would be the next stable, this would be the most stable. Right? So the branching makes tertiary carbons available, carbocations available for the charged species. So did I answer the question? Which of the following compounds will have a more abundant molecular ion peak? Okay. Oh, the molecular ion peak. Excuse me. So where would the molecular ion peak have to be? We can't split the molecule anywhere, but we can split off hydrogens. So this is a methyl group, right? It's got 3 hydrogens, right? If we break that one off, and this one goes as a free radical, then the carbocation would be here. And all we'd have to do then is a hydride shift, right? From 1, 2, 3, 4. Actually, it'd have to be a methyl shift. Hmm. Now that doesn't look quite right. It was going to take more than one step to get there, not just a simple shift. How would that happen? Okay, we've got this one gone now. That positive there. 1, 2, 3, and a positive. This is deficient, right? 1, 2, 3. So right, it gives us a positive. Then how could that resonate with this one? We want to put that one over here. The only way I can see is if we get that one, and that puts another methyl here and moves the positive down here, which would make it 1, 2. That'd still make it tertiary. Yeah, that would work. This is a methyl shift. The methyl shift would put that carbocation on a tertiary carbon. That would work. We have to form a resonance structure in order to accomplish that mission. Okay, number 37. Will the following fragmentation be more likely to produce a mass peak of 57 or 71? Okay, that looks like the molecule we were looking at before. Not quite, not quite. Okay. What's the longest chain here? 1, 2, 3, 4, 5, 6, 7. So this is a heptane. It's a 2,2-dimethyl heptane. And if we break it here, looks like it's already got a positive charge. But if we break it here, what fragment is that going to produce? Right? The following fragmentation, where does the positive charge go? It goes to the most stable fragment. So the fragment on the right would eventually put the charge on a secondary carbon. But the fragment on the left, if we let the left be the charged species, it would be much more stable as a carbocation on a tertiary carbon. So we look down at our availables. Is it a 71, right, if we put the charge on this side, or is it a 57 if we put the charge on that side? The more stable one is the 57. So it should have the most abundant peak at 57 units, atomic mass units. Oh, that's it.